time we talked about the arc length, and we discovered the arc length formula using the Riemann sum.
So we discovered the arc length for a continuous curve is going to be this integral. If you slice this curve this way, then that way here will be a dx over here, and inside here is square root of 1 plus dy dx squared. X go from A to B. And if you can slice the curve this way, then the arc length is
An integral with respect to dy.
inside this square root is 1 plus dx dy squared. And y go from C to D. And notice the match over here, the dy and dy over here, and then this dx and dx over here.
So this is formula A, and this is formula B, depending how you slice it. Now this one here, you can use either formula A or B, because you can slice it vertically this way, or horizontally the other way.
Okay, so we did some example last time. Okay, so today we have this arc length formula. So you have this BB, A to B, and we have this arc right here. And if you can slice it this way, then this arc length, let's call it L, that's equal to this integral. And then we'll put a dx over here. So that will be, in here we have this square root 1 plus the derivative of the function. So f prime of x squared. X over here go from A to B. And another way to put this is dy dx right here. Now, notice that x over here, it is just a variable. Instead of using x, I can use a t. Okay, so we can have this. Replace the x over here by t. T go from A to. Now, this 2 will be the same. Oh, wait, forgot about the square. Don't forget about the square. When we divide this formula, we actually use the Pythagorean theorem. There's a square over here. Then f prime. Okay, that's the derivative of the function. So, square root of 1 plus the square of the derivative of the function. Okay, and here's dt. So, these 2 are equivalent. Okay, it just use, instead of using this variable x, we use variable t. It's the same thing. Now we have this. I'm going to reserve this x here for something else. So over here, I have this here. Actually, I'm going to copy this. Okay, so right here. What happened over here is I'm going to reserve this x to be the variable represent any number between A and B. So I'm going to reserve this. And I'm trying to find the arc length from the starting point over here. This is starting point all the way to this point that has the x coordinate to be corresponding to this x over here. So I'm trying to find this arc length over here. So what will be this arc length? This arc length here is equal to what? What is it equal to? According to the formula right here.
Is it the same formula but integrated from A to x?
Yeah, it's the same one over here, right? Except this time it's going to go from A to x right here. So see, I reserve this x here as this upper limit right here. So that's why I don't have, you see, I reserve this x over here for that, this upper limit here. So that's why I don't want to put an x over here. So I use t here, okay? So t and t right here. So this integral here represent this arc length right here. Now, as you move this x from A to B, then this arc length here is going to change. So this arc length here is going to change as this x over here change. So when you move it here, then the arc length will go from here to here, right? And when you move it, it's going to change. So this arc length here is a function of this x over here. So it is a function of x. So it changes as x change. So when you move this x, then the arc length is going to change. So this is a function of x. Notice that this function over here is actually represented by this integral. So this might be the first time you see a function is represented by an integral right here. Now let's give a name to this function over here. Usually they use s. So let's call this s. This arc length function s. And it's a function of x. So it's s of x. So this arc length function, so I'm going to call this is an arc length function. This s of x is equal to this integral 1 plus f prime of t square and then dt, right? And t here go from starting point, the x coordinate is a, so this is a, and then the ending point, the x coordinate is this x over here. So remember, this is represent this arc length right here. Is this a function of x? As x here change, this arc length is going to change. So it is a function of x. Okay. Now, do you guys remember the fundamental theme of calculus? So what happened when what is the fundamental theme of calculus? Anybody remember? Fundamental. So that was in 110A, is in chapter 5. So what does it say? Anybody, any idea? Do you guys remember?
Like the derivative of big f of x is equal to the antiderivative of little f of x.
You got it. Okay, good. Okay, so it says that if you have a continuous function, say f, okay, so f of t, let's use this t. When you integrate this function, okay, from a to x, and after that, you're going to differentiate this function with respect to x. So differentiate this with respect to x. Then what happens? When you integrate this continuous function from a constant to x, and then later on differentiate that with respect to x, what do you get back at the end? Anyone? Integration and differentiation are reverse process, right? The fundamental thing of calculus says that they are reverse process. So what do you end up with?
F of t?
Yeah, you got it. You got the idea. So it is f of x. It's this function of x. So this is a function of x. Later on, you differentiate with respect to x. So you get a function of x. Okay. So you get back the same function, small f right here. Okay. But the variable here is x. Okay. So f of x. So you get back the same function, f of x right here. So that was the fundamental theme of calculus. Okay. Now we're going to apply this fundamental theme of calculus over here to this function over here. Okay, to this function. So we're going to differentiate this function. Okay, so over here, I'm going to differentiate this function with respect to x. Then what do you end up with by this?
F of x.
You are integrating over here. You're integrating this function over here. Later on, integrating this function from a constant a to x. Later on, you differentiate this with respect to x. According to this, what do you get? You get back to the same function that you start with. What is the function that you start with?
The square root of 1 plus f prime x squared.
You got it. It's this function, right? Except this time use the variable x, right? So you get back to this. Okay, so you get this square root of 1 plus f prime. This time we just use x and then square it. You get back the same function that you start with, which is the same as if you use this notation, the Leibniz notation. So it's 1 plus f prime of x is this dy dx. Okay, so dy dx squared, just like this, right? Now let's try to think about this. So you have this. So we end up with this ds. So if we differentiate this function with respect to x, I'm going to end up with this. So you got this, right? Okay. Now let's try to think about this ds and dx over here as differential. And then you're going to multiply this dx to this side. So you're going to end up this. ds over here is equal to, so we end it like this. We got this dx here and ds over here as differential. So, and then we multiply, and then we have this dx over here. Now we can do some algebra. Now I can square this dx and multiply inside this square root, right? So we can square this. So, and then we can distribute over here, right? So what do we end up inside the square root?
Dx plus dy square? No, dx square plus dy square?
Yes, you got it. Okay, good job. Dx square plus dy square. Okay. Now this kind of reminds you of the Pythagorean theorem, right? So in other words, you actually have dx square equal to dx squared plus dy squared. So remind you of the Pythagorean theorem. This actually, you can try to think about this. So you have this x and y, and you have this curve right here, like this. And at this point over here, and you have the tangent line. Okay, so let's draw the tangent line like this. And then the dx over here, it is, okay, the dx is this. It's a change in x over here. And the dy is actually this, the green one. That's the dy. It's a change of y along the tangent line. Okay, so that's the dy. The ds over here is ds. So this is the geometric interpretation of this formula over here. Okay, so this differential ds, when you square that, is equal to dx squared plus dy squared. Okay, right here. ds here is a change of x over here. The dy is the change of y along the tangent line. And the ds over here, it is called the differential of arc length. Okay, so the ds over here is called the differential of arc length. It is corresponding to this. Now, the arc length itself is not from here to here. The arc length is actually this blue part right here from here to here. So that is the arc length. But the differential arc length will be an approximation to this arc length right here. Okay, so try to, you can, if you have this picture, then let me understand how they relate right here. Now, we call the formula that we have before. Okay, so remember the formula we have, the arc length formula. We actually had two formulas, right? We have A and B, right? Okay, so that was the A. If you have something like that, and this is from A to B, we can represent this arc length by this integral, and we put the dx outside. This is the square root of 1 plus dy dx squared. Okay, so let me see the dx over here. X go from A to B. So that was formula A. Formula B is this one. This is the y-axis. So the curve is going to be like this. And over here, y go from C to D. Okay, so it slides this way. So the arc length over here is equal to this integral. This time we'll have dy outside. And what's inside this square root? Anyone? 1 plus what?
dx over dy squared?
Yeah. So we have dx dy squared, and then y over here go from C to D. So we have these two formulas. Now, based on what we have over here, let's see, what do we have over here? So above, we found that ds squared is equal to dx squared plus dy squared, right? So we found that. Now, looking at this one over here is actually, if you square this and distribute the dx inside, this one over here is actually going to be this ds, okay? This ds over here. And this one over here is also ds, right? So if you square this and put it inside and distribute, okay, then you also get ds over here. So the two formula, so to remember the two formula, okay, then you can put them together. So the arc length is actually equal to the integral of this ds, which is the differential of arc length. That's called the differential of arc length. So basically, you integrate this differential arc length, you get the whole arc. So yeah, so then that will help you to remember the formula. Any question here? Okay, so this is the formula that you can try to remember, right? You can put them. Okay, now let's look at this example. So we have a curve. Okay, so this is the equation for the curve. Okay, we try to find the arc length, or the arc length function. Okay, then remember we call that s of x. So I had to specify which starting point this one will be. Okay, so I'm going to take 1, 1 as the starting point. Just to help you to visualize it, I'm going to draw a rough graph of this. Okay, so the graph of this, okay, now if you substitute 1 into the x coordinate, you found out that y also equal 1. Okay, so passing 1 1 1 1 is actually on the curve. Okay, so it's going to start from 1 1. So let me label this is x-axis, this is y-axis. So 1 1 over here, and then I don't know how it goes. Maybe like this. Okay, just try to visualize it. Okay. So imagine this x over here is number greater than 1, okay? And you try to find this arc length right here. And this arc length is going to change as this x here change. When you move the x, this arc length is going to change. So I'm trying to find this arc length function right here. Okay, so what's this arc length function over here? Can someone tell me? We just went over. That's the integral of what? The square root of, now this time, this outside. So integral of 1 plus f prime of, since we reserve the t here, we reserve this x here for this, the x coordinate for this point. I'm going to use t over here, remember? Okay, so we have this t, and then square this, and then outside here it is dt. T go from where to where? The starting point
1
is,
to x.
yes, the starting point here is x coordinate is 1, so it's 1 to x. Okay, so we have 1 here to x over here. So this is the arc length function. Okay, now we just need to, but we need to substitute this, right? F prime of t. Okay, so we need to find out what this is. Okay, so we have f of x is x squared minus 1/8 ln of x. All right, so f of t is t squared minus 1/8 ln of t. Okay, so f prime of t, what does f prime t equal to? F prime of t equal to what? 2t minus 1 over 8t, right? The derivative ln of t is 1 over t, right? So this is the derivative, okay? Now we're going to substitute this into this, right? So I'm going to substitute and put it in here. So 1 plus, this is going to be 2t minus 1 over 8t, okay? And now here is dt. T go from 1 to x. Now we just need to find this integral, okay? So far, you guys are able to follow? Is it good?
Yeah.
Yeah.
Okay. All right. So now this, we need to simplify this, okay? Let's do it on this. Now in your homework, the first, the 8.1a, you actually had, maybe you had already encountered this, okay? So you have to do this perfect square, okay? So squaring this, you're going to get, what do we get? 4t squared, right? Well, the middle term over here is 2 times 2t times 2 times 2t times 1 over 8t, and then adding 1 over 8t squared, which is 1 over 64t squared, t 1 to x, right? Now you might think it's kind of complicated, right? It's actually, there's something we can use later on, okay? So we're going to make it simple, okay? So let's see what happened to this middle term right here, okay? So this middle term right here, this turned out to be 1/2, okay? That's 1/2. Now, what happened when you subtract 1/2 and adding 1? When you subtract 1/2 over here, adding 1, it'll become adding 1/2, right? So when you combine these two, Okay.
Sorry, could you scroll up?
Okay. Yeah.
Okay, thank you.
Okay. Okay. So you see that when I expand this perfect square, I got this, right? And what happened here, the middle term here simplify become negative 1/2. And this negative 1/2 combined with the 1 over here give me positive 1/2. So I will get this expression right here. Now compare this expression with this perfect square right here. The only difference here, instead of minus 1/2, it is adding 1/2. So this one here again is a perfect square. Okay, and that is going to become helpful when we take the square root, because when you take the square root of perfect square, the square and square root are going to cancel, right? Okay, so what perfect square is this one? I think in your homework you use this a lot, right? I think a couple of times already. So it turned out that this term and this term, they cancel and get a number, and you make a perfect square in here, okay? So what perfect square is this?
16.
So it's a perfect square. Well, remember when you expand this perfect square, you got this, right? You got this 3 chain over here, right? Now this 3 chain over here is kind of similar to this 3 chain over here. The only difference here is this is a minus 1/2 in the middle, and this one here is adding 1/2 in the middle. So this is going to be a perfect square similar to this, except instead of minus here, what operation should be between these two?
Plus.
Is addition, right? Okay, so addition. So we got this. This is going to be a perfect square of 2t, and this time will be addition. So this addition right here, addition, and then 1 over 8t, and this is a perfect square right here. Okay, so sometimes when you do integral, you kind of see this kind of pattern, and you see that the difference here is only this, okay? And you can recognize that this is a perfect square of that inside, and you change this to addition, okay? Okay, now when we take the square root of this perfect square over here, we're going to end up with this 2t plus 1 over 8t, right? And that's perfect, because now we take square root, we can get rid of the square right here, okay? Okay, now this is going to be 1 to x, okay? Now it's much simpler this way. So in your homework, you probably you're going to encounter this, okay? So remember this kind of trick, okay? Okay, now we can take anti-duality twin by twin, okay? So anti-duality of 2t, it is t squared, okay? And then 1/8 is a constant multiple, so 1/8. What's an anti-duality of 1 over t?
Natural log of absolute value, or just natural log of t.
Yeah, natural log of absolute value of t. It's good to put the absolute value there. Sometimes it's important, okay? So ln of t. T here go from 1 to x. Okay. Now you just need to substitute. Okay. So you're going to get x squared and then adding 1 over 8 ln of, yeah, you put the x here. You can put the absolute value. It doesn't hurt. Then minus, now you substitute 1. So 1 plus 1, 8 ln of 1. Okay. Now notice that the x over here is actually greater or equal to 1 because that, remember that graph right here, I have 1 and then the x is on the right side of 1, x is greater than or equal to 1. So this absolute value here is not really necessary. You can just put just x, okay? Let's put x over here because x is greater than or equal to 1, okay? So it's already positive, okay? And what's ln of 1? ln of 1 is what?
0.
1.
0, right? So this term will be 0, okay? So at the end, we get this, the odd length function that we're looking for, which is s of x. That will be equal to x squared plus 1 8 ln of, let's just put x, okay? Because x is greater than or equal to 1, okay? So, and minus 1. So that will be the odd length function that we're looking for. So we found the odd length function. Any question?
Are there any any like good ways to recognize a perfect square when you see one?
Oh, of course. I just went over this today in my algebra class. Okay, the good way to recognize a perfect square is this. Okay, let me put it on the side. Okay, perfect square. Okay, okay. Remember our perfect square formula. So a plus b perfect square is a squared plus 2ab plus b squared, right? And a minus b perfect square is, the middle term here will be minus, okay? So the sign here depends on this, This is a plus, and this is a plus right here. Okay, now you see the first term and the last term has to be a square. The middle term is 2 times a times b. So the one that we had before, what was the one that we had before? Let me write it down. Okay, so I have this 4t squared and minus minus 1/2, right? Okay, and then plus 1 over 64t squared. How can I recognize it's a perfect square? So first we look at this. So first we look at this. The first one here, it is a square. And the last one is also a square. The first one is a square of 2t. The last one is a square of 1 over 8t. And now this is kind of hopeful. It might be a perfect square. So we check the middle. Okay, so check the middle over here. So we use 2 times the base for the first one, which is 2t. The base for the last one, which is 1 over 8t. Okay, and it turned out that it's equal to this 1/2 over here. So that's a perfect square. Okay, so and then you write this as a perfect square by, I put it down here. Okay, so that's equal to the perfect square. Okay, the perfect square of, now here the base is 2t. The base for this is 1 over 8t. Now in between, because this sign here is minus, because it's minus, so in between it is a minus. So put a minus sign over here. Oh, the one that we have was a plus. Okay, okay, so it's a plus right here. So if it's a plus right here, then this is a plus. Yeah. If it's a minus here, then it's a minus. If a minus here, there's a minus. So that's how you recognize perfect square. So write the first and the last one as a square and see if you use 2 times this base and this base, does it match with this middle term right here? If it matches, then it is a perfect square. And you write it, the base here and the base here, and you figure out it's addition here, then addition here. If it's subtraction, then you put a subtraction here. Okay, does that answer your question?
Yes, thank you.
Okay. So now we find the arclength function. For example, if you try to find the arclength along the curve from 1, 1 to 3, comma f3, okay? So for example, so if we try to find the arclength along the curve from 1, 1 to 3, f3, then that will correspond to s of 3, okay? S of 3 right here, this one, okay? And you just substitute 3 into x, so you get 3 squared plus 1/8 ln of 3 minus 1. And when you do the calculation, that is about 8.1. So that arc length is about 8.1 along the curve from 1, 1 to 3, f3. Okay, right? Now we're done with this section. Okay, are you guys able to follow? Can I stop sharing this screen? Have you guys finished copying this?
Yeah.
Yes.
Give me a thumbs up if you are done. Okay, good. Okay, now I'm going to stop sharing. Okay, of today. Give me a thumbs up. You're still here. Okay, everybody give a thumbs up. We're still here. Let's see who's not here. Okay, thumbs up if you're here. I should take attendance this way. You guys keep on putting thumbs up so that I don't miss you. Lesson today. Okay, so the lesson is ended.